Hi, and welcome to Chapter 22's discussion on inductive reactance. So today we're going to look at the inductor. Last week we looked at the capacitor. So we'll take a look at X of L. And remember, that's the reactance is like the resistance that's associated with an AC circuit. Okay, so let's go to the next slide. Now we've already learned that how capacitance and inductance individually behave in a DC circuit, right? We looked at that with the time constant in a purely DC circuit. And now we're going to look at how the current and voltage of a capacitor and an inductor in a sinusoidal AC circuit. Now because AC voltages change continuously, there is some RMS capacitance, and a circuit having pure inductance has the phase relationship where the voltage is leading the current. So this is going to get us a concept here where we know that in a DC circuit the current took time to rise to maximum even though the full voltage was applied immediately, and then a purely inductive circuit the source voltage rises to a maximum immediately as well, leading to an exponential rise in current. So the voltage leads the current, or the current lags the voltage by 90 degrees. So this is going to be a little bit different in that capacitors and inductors operate essentially the same way in that they both store energy. However, they have completely opposite reactions to the voltage and the current. So the term Eli the Iceman is a phrase to help us remember this relationship. So E is the voltage, and it leads the current in an inductive circuit. So the voltage leads the current, so E is before I in an inductive circuit with the L. So Eli. And then ice is current, which is I, leads the voltage in the capacitive circuit, or ice. So it's the opposite. In an inductor, the voltage leads the current, and in a capacitor, the current leads the voltage. Now, if the circuit is purely inductive or capacitive, that means there's no resistance. The phase angle between the voltage and the current is always going to be 90 degrees. So we can see that in this curve, right? The distance here is 90 degrees because it's going from 0 degrees, and then when this one starts at 0, it's now at the halfway point of the positive phase, which is 90 degrees. All right. Now, this Eli the Iceman is going to help you. Just remember that Eli is voltage leads the current in an inductor, and then ice is current leads the voltage in a capacitor. All right. Now, the term inductive reactance is when the current flowing through an inductor continuously reverses itself, the AC source, the inertial effect of the CMF, is greater than with DC. So the greater the amount of inductance, the greater the opposition from the inertia effect. Also, the faster the reversal of current, the greater the inertial effect. So we can calculate this. So instead of X of C, we're going to use X of L. Now remember, inductors will pass DC and block AC, and the capacitor is the opposite. So remember, X of C equals 1 over 2 pi FL, or FC. In an inductor, XL equals 2 pi FL, where X of L is the inductive reactance, the frequency is in hertz, the inductance is in Henry, and then 2 pi is 2 times pi. All right, so let's look at this. So to determine the inductive reactance of a 20 Henry coil when the frequency is 60 hertz. So again, you just take 2 pi FL, 2 pi times 60 times 20 is 7.54 kiloohms. And then determine the inductor current if the source is a 120 volts AC for the previous. So we know X of L equals 7.54 kiloohms. So now we're going to take I equals voltage over the inductive reactance. So 120 volts divided by 7.4 kiloohms equals 15.9 milliamps. All right. Now X and L can be determined by Ohm's law. If the frequency is known, L can be calculated. So L is going to equal X of L over 2 pi F. So it's just modifying the formula. So if the source voltage is 24 volts AC and the inductor current is 10 milliamps with the frequency of 15 kilohertz, determine the value of L for the circuit. So the first thing you want to do is figure out the inductive reactance, which is VL over IRMS is 2.4 kiloohms, and then solve for the inductance where X of L equals L times 2 pi F, 2 pi frequency. Now divide that around and you get L equals X of L divided by 2 pi frequency, and you end up with 25.58 millihenries. All right, so it's just a little algebraic manipulation there. Now, frequency can also be solved by solving for F, and you can determine that there. Okay, so some of these are really straightforward. Now, just like in a parallel resistive circuit where RT equals 1 over the sum of the reciprocals of all the resistors, it's the same in capacitive parallel circuits. So the inductive reactance equivalence is going to be 1 over the sum of 1 over XL1 plus 1 over XL2 plus 1 over and so forth. So that's it's just like a parallel DC circuit. All right. Now there is another formula here, or another factor, which is the Q factor. So the quality factor, which is a merit called the quality factor. This is an indication of the coil's ability to store energy and release it rather than dissipate heat. So it's also a function of how inductive a coil is compared to its internal resistance. Now, the greater the internal resistance, the less ability the coil has to produce and induce voltage. So it needs to have a higher internal resistance, then it will store that energy. All right. Now, Q can be determined as the ratio of reactive power to real power, or the power in the inductor over the power of the reductive, the Ri. So that's going to come out to I squared XL over I squared Ri, which is X of L over the internal resistance. All right. So a coil has an X of L of 800 ohms and an internal resistance of 12 ohms. Calculate the value. So that's just going to be 800 over 12, which is 66.7. Okay. So Q is unitless. It doesn't have a value. It's just saying that the X of L is 66.7 times greater than the internal resistance. So a Q of 10 or more is considered high. So the 66.7 would be a very high Q factor. All right. Now at low frequencies, the internal resistance is just the DC resistance of the conductor in the coil. And then as the frequency increases, the RF coils exhibit losses greater than those from the conductor resistance. And then at higher frequencies, the effects of eddy current, hysteresis, and other losses become more apparent. So losses occur at a high frequency known as AC resistance in order to differentiate them from DC conductor losses. All right. Now recall that at higher frequencies, the phenomenon known as skin effect occurs. Skin effect reduces the conductor's cross-sectional area, thus increasing the resistance. So at high frequency applications, the transmission line is hollow because very little current flows in the center anyway. All right? Now we can say that collectively hysteresis, eddy current, and skin effect make up the AC resistance of the coil. So when this is added to the DC resistance, we have a new value that is called the effective resistance, or RE. And the Q factor can be determined by dividing the inductive reactance by the effective resistance. So determine the Q of a coil when X of L is 500 ohms and the effective resistance is 50 ohms, and that would be 500 divided by 50, which would be 10. Okay? So that's chapter 22, and we'll keep going with chapter 23 next week. And I'm going to start making these videos beforehand. Some of you had asked Professor Lage if we could do that, and we certainly can do that. So I'll start pumping these out, and we'll have probably the rest of the semester done this week. And then you can work ahead on, or look ahead on the lecture lab, the lecture material, so you'll be better prepared for the labs. All right, take care, and I'll talk to you later.